Niels, who is from KU Leuven, Belgium, and he was giving his presentation on controlled graphite functionalism by photocatalytic oxidation for rationally engineered electrocatalysis. Yeah, Mr. Niels, can you share your screen, please?
Yes.
Yeah, you can start your presentation.
Okay. Good. Can you see my screen?
Yes.
Okay. So let me first introduce myself shortly. I'm Niels, working at KU Leuven, University of Leuven. I'm now in my last year of PhD research, and I'm mainly working on carbon materials and photocatalytic oxidation to valorize them and make them more interesting for applications like electrocatalysts and optoelectronic applications. So the title of my presentation now is the controlled graphite functionalization by photocatalytic oxidation for rationally engineered electrocatalysis. So the outline of this presentation is as follows. So I will first start with a small introduction. Then I will tell more about properties of graphitic carbons and graphite, which are the main materials of my research because of very interesting properties. Then I will tell more about photocatalytic synthesis methods, the method I use, followed by the results and some key messages to end this presentation with. So first, what am I doing exactly? So I'm performing a controlled and mild oxygen functionalization of graphitic carbon materials. So I'm using a UV-driven photochemical method, so using photocatalysis for my rational electrocatalyst design. So after the photooxidation, I further activate the materials by a heteroatom doping method for at the end becoming and achieving an efficient carbon-based electrocatalyst material. So my research is focused on the photocatalytic oxidation of natural graphite as well as synthetic graphite in many forms. For example, we have the powders, natural graphite powder, also HOPG, or highly oriented pyrolytic graphites. We have graphite fibers and also graphite rods. We all use these materials. So I'm using an anatase titanium photocatalyst material because this is the most active one in view of oxidation reactions. And I'm also using a controlled gas atmosphere with oxygen and hydrogen. Water vapor reagents at a relatively low temperature, so it's not thermally driven, it's by UV driven. What is the research purpose? So the synthesis of a photocatalytically oxidized graphite material with a mild oxidation degree and still a high electron conductivity, because this is the most interesting thing in terms of electrocatalysis. So to become an active electrocatalyst, that's the way we also synthesize our materials. So how is this done? In a first step, we do the oxygen functionalization by photocatalytic oxidation. And this is followed by a subsequent step, the heteroatom doping, to further specific tune the material and to make them electrocatalytically active by having dopants, very active dopants. So in this way, we tune the catalyst design parameters. As you can see here on this image, you have many parameters to take into account, like the electronic structure, stability also of the material, selectivity, of course, for the end reaction you want. So this tuning is very important, and this is mainly based on the feedback we get from our sample characterization. We use many methods, as you will see later on in this presentation. So first, the graphite properties. Why do we use graphite or graphitic carbons in general? Graphite is a very stable carbon form. It's actually the most stable carbon form among all carbons, and it's highly abundant and also not very expensive. It's one of the most occurring carbon elements in the Earth's crust, I think the 15th most abundant element. So graphite has very high electrical conductivity, in plane electrical conductivity, so in this direction. And also, of course, the excellent chemical tunability is very nice to work with. So it has also a very high electrochemical active area. That's a typical property of a lot of carbon materials, that they can be very active due to the accessible surface area. And most carbons are also characterized, and especially graphite also, for their low selectivity for competing reactions in electrochemical reactors. For example, the HER, the hydrogen evolution reaction, is very often not desired because you want to synthesize other chemicals electrochemically. And of course, graphite has also a very high resistance towards corrosion, mechanical forces. It's a very stable material, as was said already here. As you can see, graphite is also composed of the building blocks, which are graphene sheets. These are separated by an interlayer van der Waals distance of 0.3 nanometers. And the carbon-carbon distance in plane is around 0.14 nanometers. This is how graphite looks like by electron microscopy. So at the left side, you can see natural graphite powder particles from different sizes, which are really a bit more disordered than the synthetic form of graphite. Here at the right side, you see the synthetic HOPG, which is far more oriented and better aligned, very nice stacking here. And you have really like a book composed of thin graphene sheets. This synthetic graphite form has also less structural defect sites, like edge planes, vacancies, so structural defects, which are more common here in the natural graphite form, but still are only a minor part of the entire material. So electron conductivity, as I said, this is a very important property in view of the end application as an electrocatalyst. So the electron conductivity of graphite is very high. This is because of the sp2 hybridization. So graphite has a trigonal planar geometry. So every carbon atom in the graphite plane is bonded to 3 other carbon atoms with sp2 hybrids, orbital hybrids. So as you can see, one s orbital is combined with 2 of the 3 p orbitals in the plane of graphite, so in the xy direction. So you have 3 sp2 orbitals in plane. Of course, there is a 4th p orbital in the z direction, which is not taking part immediately in the direct carbon-carbon bonding in plane. This also contains an electron. So what you maybe not know, carbon has 4 electrons, which are, it's a tetravalent atom. So 4 electrons can bond with another carbon electron. So 3 of these 4 carbon electrons are in each of this sp2 orbital hybrids, but the 4th one is here in the z direction, so can actually freely move, is divided over the 3 other carbon bonds. So this 4th electron has a 33% double bond character. It's actually a delocalized p electron, which can really move over the plane without any energy loss. So it's often called also the ballistic transport of electrons, It's a very nice property of this material, of graphite, and it generates then, of course, the very high electron conductivity or electrical conductivity. Also, a high thermal conductivity is created by this property. So here you can again see the 6 electrons of carbon, which are divided in all these orbital hybrids and orbitals. So now the synthesis method. So in a first step, as I said, we do the oxygen functionalization by contact or remote photocatalytic oxidation of graphites. So here you can see the sample setups we use and which are working the best. So at one side, we use a front irradiation configuration. So when the UV light is illuminating the graphite layer on top of the titanium dioxide layer, here you can see a contact mode setup. On the other hand, we also use the back configuration, which is actually reversed. So the samples are here different because the titanium dioxide layer is on top of graphite. As you can see here in a remote mode setup. So this is remote mode because there is a polyimide spacer material in between the 2 layers. All this, so the photooxidation is based on the photocatalytic mechanism. Maybe you are known with this mechanism. So UV light is exciting an electron from the valence band to the conduction band. This creates holes which have actually an oxidizing power and also can already oxidize, for example, reagents like water vapor into a more reactive hydroxyl radical. Here, on the other hand, you can see also excited electrons, which also have a reactive power, but are reducing the oxygen reagents into a superoxide anion radical, which makes very reactive reagents to further go into interaction with another material, for example, in our case, or carbon material or graphite layer. This is all located and positioned here inside of a photoreactor, which is contained and sealed here by a glass plate. And you have a UV lamp shining from the top. As you also see here on this slide, here are the 2 photoreactors in our lab. So the advantages of these methods are the following. So you have an excellent process control. The process control is actually great. You can tune the oxidizing gas mixture, temperature, reaction time, also the distance between the layers, the amount of catalyst and carbon powder or carbon material. We have at the same time a mild gas phase oxidation because that's also very important and is quite special because most graphite oxidation methods are more aggressive and harsh. For example, the common Hummers oxidation method is a very harsh and not so environmentally friendly metal. It uses strong mineral acids like sulfuric acid and also strong oxidizing agents like potassium permanganate. So it's really a very destructive method for the end material, which is of course not very interesting for an end material like an electrocatalyst, in which you want that conductivity to be high. Also, our method provides a very uniform oxidation of the graphite layers, and it's a very reproducible method, especially the remote oxidation method. It's also eco-friendlier, of course, and it allows remote photocatalyst control and a photocatalyst that can be easily reused without degradation or without activation loss. So here is shown schematically how this is done. Also, so here our reagents come into the reactor. After the reaction, we have an outlet gas that is detected for their components by UV or an infrared detector. This allows us to know what are the CO2 and CO concentrations that are produced, and it enables calculation also of the product yields. after reaction based on the initial mass that was loaded into the reactor. In a second step, we use that photocatalytically oxidized graphite product to further activate it by heteroatoms, the doping as it's called. So we use metals or non-metals like these ones listed here. And we use many different methods and try to develop the best method in terms of our end reaction. So as you can see here, we use aqueous solutions of our metal containing precursor. We immerse the carbon products and also do a heating step or stirring step. And mostly we end with a drying step or a calcination or pyrolysis step to reduce, for example, oxides on the surface and make it more active in the end. Another very effective method is the solvothermal or hydrothermal method, which is often composed of an ultrasonication step and of course a high temperature treatment in solution in an autoclave, and also followed by washing and drying. Also an effective method is the thermal annealing method, which contains soaking or immersion of our carbon product in a precursor solution, and also pyrolysis step at very high temperature, but in an inert atmosphere. That can also be argon, for example. This is also followed by washing and drying. And another method, which may be a bit different, is electrodeposition of our components or species, the dopants. And of course, we have also combinations of different methods, which can lead to a very efficient, good method. At the end, we want to test, of course, all these materials in the electrochemical cell for their activity. Here you can see on this slide how this doping step is performed in the lab. So here at the left, you can see how a molybdenum doping is done. You can see it's often in liquid phase and also evaporating things. In this case, we have molybdenum trioxide as the active electrocatalytic center. This can also be molybdenum disulfide, disulfide, if you do a sulfurization step. Another dopant can be boron. For example, the doping of oxidized carbon paper which are actually graphite fibers. So this can be doped with boron, and you can create in the end a boron doped or boron oxide doped active electrocatalysts. So the species are then bonded actually with or contained in the carbon lattice. And so you create an active electrocatalyst. This is of course always controlled or checked by characterization methods like high resolution scanning electron microscopy, also atomic force microscopy. AC means alternative contact or tapping modes. Raman spectroscopy is one of the most useful structural characterization methods, and you also have X-ray, electron spectroscopy, and thermogravimetric analysis, which allows to have a more chemical analysis to know the chemical composition. This is also often complementary to Fourier transform infrared spectroscopy. So these techniques are more chemical based, and these give you the CO ratio, also the elemental composition of your material, the weight percentages, thermal stability, and functional groups on your material. So this is very important to have feedback on how the first two steps, the oxygen functionalization followed by the doping, how this was done and what is the end result, and to work each time back. So results are shown here. First, for step 1, the photooxidation process in gas phase. So first, the question is, what is the effect of all these gases and vapors inside the gas mixture. If you have more oxygen, of course, this is logic, you have a higher oxidation degree, but a lower POG yield. POG is photocatalytically oxidized graphite. So you have to find the right balance between the yield and also the oxidation degree. Nitrogen oxides have also been used in the past in the oxidation gas mixture, but they turned out to be too oxidative because the degrees of POG yield was too strong, while not actually increasing the oxidation degree in the end material. So this was not interesting. The rate was too fast. You immediately gasified graphite into CO2 and CO, which is not our desired purpose. Also, the effect of reaction temperature and UV illumination was tested. The temperature is creates a higher yield at lower temperatures, so this was very interesting. Also, at these lower temperatures, we had preservation of excellent oxidation degrees, so this was a very nice result. Also, the time is investigated and shows to have also a strong effect on oxidation degree, but it also decreases the yield. So in that case, we also have to find the right balance. A good balance is often when the yield is more than 65% and also an oxidation degree of around 0.3 for the ID over IG ratio. This is related to Raman spectroscopy, and I will explain this later on in this presentation. It's actually a measure for the oxidation degree. So ideally, we have a photooxidation under 70 to 80% of oxygen in absence of nitrogen oxides like NO2 and NO at this temperature, so a relatively low temperature compared to a lot of other oxidation reactions. Around also the duration around 96 to 120 hours of UV illumination. Then in this table, you can see the advantages and the drawbacks, the contrast of contact oxidation versus remote oxidation. Contact oxidation often creates a less uniform oxidation and of course also creates a difficult product separation between our POG and our photocatalyst layer. Sometimes it also generates two defective POG areas, but it's between brackets because that depends on which starting material you use. For example, natural graphite is less oxidation resistant. It's actually easier to oxidize than synthetic graphite like HOPG, which is a bit more refractory. So with HOPG, you mostly don't have that two defective POG areas. The pros of contact oxidation, or the advantages, is the higher reaction rate. You don't have an interlayer spacing through which the reagents have to travel, so there is immediate contact, so the accessibility and the activity is a bit higher. So remote oxidation has a few drawbacks, but not so much, actually small drawbacks. These are a bit lower reaction rate and the use of a spacer material. This is only minor. The big advantages of remote oxidation are, of course, the uniformity, which is much higher, and also a better reproducibility, and of course, the ease of photocatalyst separation and reuse. So in remote mode photocatalytic graphite oxidation, we have the most technical advantages, also technological advantages. So in terms, of course, also of our end application as an electrocatalyst material, which has to be pure and uniformly modified, we recommend remote mode photooxidation. At this slide, you can see the morphological change of our graphite materials. Here, natural graphite upon photocatalytic graphite oxidation. shown by scanning electron microscopy images. Here you can see the pristine graphite, so not oxidized. Here you see the smooth layers again. This is converted into very rough graphite surfaces after photooxidation. At this image, you can see how a contact oxidation affects the surface. So here you can see mostly at the edges, very abundant surface blisters or very large bumps and protrusions at the edges of the graphite material. At remote oxidation, we see a more uniform blistered surface due to the distance between the photocatalyst and the graphite layer. It creates a more reproducible uniform oxidation. As you can see here on this image, the spacing we used is only 25 micrometers. And the photocatalyst is anatase, as you can see here, in contact with our graphite material. So first surface blisters are created on the graphite edge planes, as well as on the smooth basal planes, as you can see here on this slide. For HOPG or synthetic graphite, we see actually quite the same effects. This is very clear here on this slide. So remote oxidation creates a uniform modification of the surface by creating large surface blisters. Also, some small blisters are noticed in between the larger blisters. Here in this case, we used also nitrogen oxides, which leads to the cracks and the removal of carbon material, actually a loss of material due to gasification into carbon oxides, CO2, CO. So remote oxidation produces a very stable covalently modified POG with surface blisters. The topographical change, which was already a bit seen by SEM, is here shown by AFM. As you can see here, the smooth HOPG plane is very flat, but this becomes more bumpy and decorated with surface blisters after photocatalytic oxidation. This is shown here, where we have blisters of around 10 nanometers in height. The width can be very large. The width can be from also 10 nanometers to even 600 nanometers. Here, this is shown here with a height profile corresponding here to this 2D topography image. Also, we create irregularly shaped blister clusters. And these are often connected by networks of smaller blisters. So a strong increase of the surface roughness is achieved and observed here. This is actually a consequence, or shown here, by the structural characterization method Raman spectroscopy. So this transformation of the flat sp2 carbon hybridization into sp3 hybridized carbon is shown by Raman spectroscopy. The typical Raman spectroscopy spectrum of graphite materials and a lot of other carbon materials are characterized by a D and a G band. So the D band represents the defects, structural defects and sp3 hybridized carbon due to bonding, for example, by oxygen, as you can see here. A G band stands for the sp2 hybridization. So the in-plane stretches of sp2 carbon bonds. So if you have pure graphite, pristine graphite, like this black curve, the black spectrum, you have a very strong G band, but almost no D band. This small bump is due to the intrinsic structural defects, like the small areas at the edges or a vacancy, which can always be present. So this tells more about the oxidation degree by taking the ratio of ID over IG, also the defects content and the number of layers. As you can see here, there is a strong emergence of the defect activated bands D and also DXN, which is very strongly related to the D bands due to the transition of the planar sp2 carbon bonds, which you can see here, into tetrahedral sp3 bonds by covalent oxygen bonding. So this covalent oxygen bonding is then confirmed by more chemical analysis of the POG product, actually by XPS and TGA. XPS is a very surface sensitive technique providing chemical compositions of materials. Here you can see a strong peak here around binding energy of 533 electron volts. This is corresponding to the oxygen peak and CO oxygen bonding, carbon oxygen bonding. So here we have a proof, a confirmation of CO double bonding. And also here there is a shoulder at the left side, which confirms the CO single bonding. This is also represented in the C1s XPX spectrum, which shows here C carbon oxygen double bonding by this peak and also CO single bonding by the shoulder, which is more present than here in the reference spectrum of natural pristine graphite. Also, chemically analysis is provided by TGA, which actually shows the temperature stability, the thermal stability or lability of chemical functional groups. For example, oxygen functional groups are often less chemical stable and start to decompose from a certain temperature. As you can see here, this POG1 has a weight loss of around 12 weight percent, which corresponds to the loss of carbon CO2 or CO, so due to the loss of oxygen containing functional groups. So this is also a confirmation of the oxygen functionalization, but it still shows that the temperature stability is very high compared to other graphite oxides or more harshly oxidized graphite materials like in the Hummers oxidation method, which is actually ideal for our electrocatalyst application. So we have a moderately oxygen functionalized graphite with covalent CO and C double bonded to O bonds. So this product, POG, is then doped by heteroatoms. We have shown by different techniques that there was a successful incorporation of metal and also the non-metal species like boron into our carbon lattice. This is shown by SEM, for example, here the graphite fibers or graphite particles. Also EDS or energy dispersive X-ray spectroscopy shows very strong peaks for dopants like bismuth or molybdenum or selenium. And also XPS shows characteristic spectra for the presence of metal species and other active dopants for our electrochemical reaction. So the electrocatalyst test happens in our electrochemical cell in the lab. We use chrono and barometric measurements at a quite low voltage to preserve the beneficial CO bonds, which are often also electrochemically active as such. That depends, of course, on your end reaction. Also, we use ion exchange chromatography to determine the electrocatalytically produced amounts. And in the lab, it was shown that we already obtained promising yields and Faradaic efficiencies of our electrocatalyst materials, but this still needs to be further developed and needs to be higher to have a really competitive product and reaction that can compete with current industrial reactions at this moment. So some key messages of this research is that we have performed a mild and controlled graphite oxidation using titanium dioxide photocatalysis and oxidative gas mixtures. We have a remote photocatalytic oxidation that provides a powerful avenue for product end use. Also, we have shown that we have uniform oxygen functionalization of the graphite surface structure via our photocatalytic process. We have a moderate oxidation degree and a high stability in our product for efficient carbon-based electrocatalysts. And the reactivity of the material was increased to chemical reactivity by the presence of these oxygen functional groups and also our chemical dopants. And last, a high modifiability of our process as well as our products enables further electrocatalyst performance increase and optimization to work on in future research. Finally, I would like to use this final slide to make also some promotion for our UCAT network, or UCAT, which is the Young European Catalysis Network. This is a young team of motivated researchers which are sharing science in a nice way and come together to have interactive discussions. We also organize our events. So if you are interested to join this network, you can always send emails to this email address or have a look just on this website. And finally, I want to thank you all for attending my lecture, and I want to thank you for your time. And feel free, if you have any questions, please ask me. Thank you.
Yeah, participants, any questions regarding Mr. Niels Ostyn presentation?
Sorry. Yes. Okay. Sorry, can you repeat the question?
Yeah, just I'm asking the participants, are they having any queries? I mean, any questions for you?
Sorry, my sound was a bit too low. I will make it a bit higher. Yeah. Can you repeat it once? Sorry.
I have a question.
Yes. Please feel free to ask me your question.
Yeah, can you hear me?
Yes, I can hear you well.
Yeah. Okay, so I am Javier from UCL. So it's just maybe a suggestion for, because you are considering the oxidation. So have you thought about maybe designing experiments as TPO with different oxidative conditions from gas mixtures and so on? Is something that you may consider or you would like to consider?
Yes, that's actually, we can consider that. We didn't try that in the past, but we have a lot of opportunities to further modify also the gas mixture and to have different reactions inside our reactor, because we have connections with different tubes and also a big reactor that also have the potential to connect all the reagents, for example, nitrogen containing reagents. So we can actually also completely change our reaction mixture.
Yeah, I think it's because it would be interesting to see in different kind of atmospheres, let's oxidative atmosphere, to check if it changes the performance that you obtain in terms of the oxidation. So it could be a good suggestion for future. Yeah.
That's a very nice suggestion. Thank you. Yeah.
Thank you.
Okay.
Any questions? Yeah. Thank you.